All right, let's just get right into it. Welcome to this explainer. Today we're tackling what is literally one of the most high-stakes, sweat-inducing situations in software engineering, the production outage. Look, if you've ever been on call, you know exactly what I'm talking about. It's 3 a.m., your pager is absolutely screaming, the system's completely down, and every single minute is burning thousands of dollars. We've all been there. So today we're going to break down the exact frameworks, the observability tactics, and the mental models that elite, senior engineers use to cut right through that chaos and debug production so much faster than everyone else.
To do that, we really need a fundamental mindset shift, perfectly captured by this quote from AWS. Failure is inevitable in distributed systems. You know, when you're operating at true scale, components are absolutely going to break. Networks partition, hardware fails, deployments have bugs. It's just a fact of life. Functioning despite those failures, that's not some miraculous recovery, that's just your normal mode of operation. We really have to stop designing systems and honestly, training our brains for this perfect world that just doesn't exist.
And that brings us to the million-dollar question, right? If everything is constantly breaking, why do some engineers confidently resolve these massive failures in a matter of minutes, while the rest of us might spend hours just spiraling in this reactive panic? Well, the secret isn't that senior engineers magically type faster or have some kind of sixth sense. It's that they use a highly structured, observability-driven framework. Basically, they don't guess. They hunt for signals. Here is exactly what we're going to cover in our masterclass today. First, the anatomy of an outage. 2, finding the signal over system noise. 3, why you must mitigate first and investigate later. 4, a real root cause analysis framework. And finally, number 5, proactive system hardening.
Okay, let's jump straight into part 1, anatomy of an outage.
To understand modern outages, we have to look at the sheer scale we're dealing with. At modern hyperscale, think about Uber's backend architecture. A single user request, like just tapping a button to book a ride, might actually traverse up to 500 discrete microservices. That one action can fire off over 30,000 remote procedure calls. Just let that sink in for a second. At that level of complexity, guessing the root cause of an outage is, well, mathematically impossible. You literally cannot hold the whole system in your head. A minor hiccup in one tiny, seemingly non-critical service can cascade and take down your entire core business. And that complexity perfectly sets the stage for the butterfly effect in distributed systems. A classic example is the dreaded retry storm. Imagine time zero. You get a localized failure in one small client, just a tiny blip. But at plus 100 milliseconds, that failing dependency automatically triggers retries. Fast forward to plus 500 milliseconds, and the downstream clients of those original clients also start retrying. By the 2-second mark, you've got exponential traffic growth. Your services become totally overloaded because they're suddenly trying to serve normal traffic plus this massive, compounding tsunami of retry traffic, all while they're already degraded. In literally seconds, a tiny localized blip multiplies into a massive, cascading system meltdown.
Which leads us perfectly to part 2, signal over system noise. Because when that meltdown happens, how do you see clearly?
Look, the absolute most crucial difference in triage is how you look at your data. A more junior approach often relies on average latency. They'll look at a dashboard, see a 50 millisecond average response time, and think, hey, everything's totally fine. But here's the truth. Average latency is a liar. It completely hides the fact that 1% of your users might be suffering through 2-second delays or constant timeouts. Elite engineers, they stop celebrating the average and they obsess over the tail behavior, specifically P99 or P99.9 latency. Measuring the P99 tells you exactly what the absolute worst 1% of your users are experiencing. When you're running massive systems, rare slow events are no longer rare. You've got to optimize for the tail end.
So, if you're ever staring blankly at a wall of dashboards at 3 a.m., half awake, and just completely overwhelmed by a sea of red flashing lights, you need to pull back to the 4 golden signals. This is your lifeline. To instantly gauge system health, you check traffic, how much total demand is actually hitting your system. Errors, what's the rate of failing requests? Latency, how long is it taking to service those requests? And saturation, how full is your system? Are your CPUs pegged, or are your connection pools completely maxed out? If you just focus on those 4 signals, you instantly have a compass in the dark.
And when things are running slow, performance experts like Brendan Gregg champion this absolutely critical concept. Most people only look at on-CPU profiling. That just shows what the code is actively executing. But if you only look there, you're missing where the time actually goes. Senior engineers look at off-CPU profiling, because in production, threads spend an enormous amount of time doing literally nothing but waiting. They're waiting on database locks, waiting on disk I/O, or waiting on downstream API calls. And that hidden waiting time, that is very often what directly translates into your user-facing latency.
All right, moving on to section 3, and honestly, this is probably the most vital piece of advice in this entire explainer. Mitigate first, investigate later.
Listen very closely to this rule from Gergely Oros, a seasoned engineering leader who operated massive systems over at Uber. Mitigation now, investigation tomorrow. Look, during an outage, your adrenaline is absolutely pumping. Let's say you actually find the bug in the code that caused the crash. The temptation to write a quick, slick fix, commit it, and shove it straight to production is overwhelmingly strong. You have to resist that urge. Your immediate job as an on-call engineer is just to stop the bleeding, not to solve the puzzle.
Let's break down why. Mitigating simply means rolling back the bad code to the last known good state, or maybe failing over to another data center. It restores service instantly. But fixing forward, that means writing brand new code during an ongoing chaotic outage. The immense danger here is that you are basically doing force testing in production while the system is already unstable. Fixing forward is the ultimate recipe for introducing a second, much worse cascading failure right on top of the first one. So stop the bleeding, roll it back. You can investigate the bug tomorrow when you've actually had a cup of coffee and some sleep.
Okay, so it's tomorrow. The dust has settled. Now we hit section 4, the root cause analysis framework. Elite engineers use the 5 whys framework to make sure they aren't just treating surface symptoms. Let's trace a real-world example here. Why did the outage actually happen? Step 1, a code bug was deployed. Okay, why? Step 2, well, the code reviewer missed it. Why did we rely solely on a human reviewer? Step 3, because there wasn't an automated test for this specific use case. Okay, why was there no automated test? Step 4, because it's incredibly difficult to test this flow locally. Why is it so difficult? Step 5, because we have a systemic lack of dedicated test accounts in our overall architecture. Do you see what just happened there? We moved all the way from a surface-level human error, literally just blaming a reviewer, to uncovering a deep, systemic architectural flaw that desperately needs to be fixed. That right there is elite root cause analysis.
Finally, section 5, proactive system hardening. How do we stop this from happening again?
The ultimate answer is chaos engineering. This is, without a doubt, the pinnacle of senior-level practices. Instead of just sitting around waiting for things to break randomly, you purposefully and intentionally inject failures right into your system in a highly controlled way. You artificially add latency, you go in and reboot servers, you literally kill database replicas, all to verify that your system can actually tolerate these realistic disruptions without ever impacting the end user.
Let's look at how this fits into the broader AWS resilience lifecycle. The overall flow goes from setting your objectives straight into design and implementation, and then we hit a really critical phase, evaluate and test. This is exactly where chaos engineering lives. You don't just build a system and cross your fingers hoping it's resilient, you have to actively test its resilience. Change is a constant. Networks evolve, dependencies shift all the time. Evaluating through chaos engineering ensures your assumptions about failovers and timeouts actually hold up out there in the real world.
And keep in mind, this isn't cowboy engineering. It's a meticulously controlled experiment. Think about the timeline of an injection. First, you start your load generation and establish a steady state. You absolutely must know what normal looks like. Then, you inject the failure. Immediately, you observe the application performance taking a hit. You're watching your dashboards, checking those golden signals we talked about. Then, and this is the crucial part, you explicitly stop the failure. The application performance recovers, and finally, you end the load generation. It is a precise, scientific process designed to prove your system's exact resilience boundaries.
As we wrap up this explainer, I really want to leave you with this core takeaway. Performance is a property of the entire system. Stop looking at lines of code and start looking at the architecture. Honestly, whether you're dealing with a massive retry storm, analyzing your P99 latency, or running a chaos experiment, you just have to zoom out. Senior engineers don't just fix bugs, guys. They engineer the entire request path to be predictable under heavy load and partial failure.
So, I'll leave you with a bit of a provocative question. When that pager goes off at 3 a.m. next week, what are you going to do? Are you going to panic and start wildly guessing? Or are you going to check your golden signals, look at the P99 latency, mitigate the issue immediately, and then calmly hunt down the systemic root cause the very next day? The choice is entirely yours. Thanks so much for joining me on this explainer, and hey, good luck out there on call.